What is a reference frame? What is this thing Dr. Ferrone keeps talking to us about? In technical terms, a reference frame consists of a fixed area, reference point, and a specific basis that are used to give a unique set of fixed measurements. That's all great, but what does this really mean though? And how is this useful? Really, looking at examples is the best way of understanding exactly what a reference frame is. Here's a great example that we saw in Homework 2 with the Sun, Earth, and Moon system. If I were to ask you, how would you describe the motion of the system, what would you say? The thing is, you can't really answer that question because it really depends on the question you're asking yourself. For example, if you're asking yourself, how does the Earth, Sun, and Moon system move throughout the universe? You would find your own specific motion equations. If I were to ask you, how does the Earth move around the Sun? Again, those would be completely different numbers than before. So how would you compute the motion of this? The thing is, you have to use reference frames. So again, a reference frame consists of a fixed area, a reference point, and a unique basis. Because each reference frame is unique to one another, the motion of one object relative to one reference frame will not be the same when computed relative to another reference frame. For example, if you're in orbit around Earth, the speed of your orbit relative to Earth is not the same as the speed of your orbit relative to the Sun, and this is a very important distinction to make. In engineering, this is useful because you only have to use reference frames that will directly influence your result. If you're a satellite in orbit around Earth, you're concerned with your motion relative to the Earth, not the Moon. If you're an aircraft, you're concerned with your motion on Earth, not your motion relative to the Sun. This is a very important distinction in understanding reference frames. Train motion is a good example of how reference frames work. At the beginning of the video, you can tell that the train we are on is moving, while the other train is fixed with respect to the Earth. When the background goes away, however, we can no longer tell which train is moving, which gives us a good visual of how things move with respect to our reference frame. To us, it seems like the other train is moving and that we are the ones that are actually not moving, but we know that we indeed are. Every day that you walk or bike to class, you pass a lot of people. But the question is, are you passing them or are they passing you? This is actually a reference frame problem in disguise. In your reference frame, you were stationary, and everyone and everything else is rotating and translating around you. In their reference frame, they treat themselves as stationary, and you are passing them. In the Earth's reference frame, it is stationary, and you are both passing each other. Again, it all depends on whatever reference frame you are using. There's only one problem with everything that I've been saying so far, and it's the fact that you know that you are moving. I've been telling you that your motion in your reference frame is zero, but you know for a fact that your body is walking while the Earth is rotating and orbiting the Sun, which is also moving through the universe. The reason I can tell you that your motion in your reference frame is zero is because your reference frame is a moving reference frame. It is not an inertial reference frame, which is an unmoving reference frame. The perfect inertial frame has not been discovered because we do not believe that there is a center of the universe that is unmoving. But we can treat the Sun as an almost perfect inertial frame by using the stars, which are practically unmoving, as coordinate axes, and the center of the Sun as a reference point. It is important to understand how these reference frames are different, and this is due to how each are related to Newton's laws. An inertial frame exists because of Newton's laws, which actively predict the existence of an inertial frame. But as I said before, it has not been discovered and it's only been hypothesized. A non-inertial reference frame has nothing to do with Newton's laws, and are only a purely mathematical concept created by comparing motion between multiple frames. For example, if I were sitting across from you and rotated 360 degrees in my chair, in my reference frame you would have accelerated and rotated around me. But you feel no such force caused by the acceleration, which proves that Newton's laws are not connected to non-inertial reference frames. Even though mathematical expressions can be found to describe our relative motion, our movement does not directly affect each other. A great game that really explains the differences in reference frames is Kerbal Space Program. Simulated here, when a rocket launches, it performs a maneuver called a gravity turn in order to get in orbit around the Earth. As seen here, when I fix my reference frame on the rocket's center and begin the maneuver, Earth seems to fall away and rotate, while the rocket seems stationary. This is because I am in the reference frame of the rocket. In the Earth's reference frame, the rocket is moving upwards and rotating to perform the maneuver. Here I am attempting a docking, the process of which is heavily dependent on reference frames and computing motion of the two bodies relative to each other. When I pull up the game controls, you can see that in the reference frame of the target, I'm moving about half a meter per second towards it. But the game allows me to change reference frames easily with a click of a button. Because of this, I can switch to orbit, or the reference frame of the center of the Earth, or surface, which is the reference frame of a point on the center surface of the Earth. As you can see, all values which correspond to the same motion are different in various reference frames. So how do you compute all of these different values in all of these different reference frames? And how do we get all of those crazy equations we always get in class? Let's take this example for one. Let's take reference frame R1 with point 0.01 and basis ij. let's take reference frame R2 with point O2 and basis KL, and then let's have another point M that we're trying to find the motion of. Let's have reference frame R1 be unmoving and fixed in the page. Therefore, R1 is our inertial reference frame in this instance. Let's have point O2 be translating with speed VO2 and rotating with angular speed omega. Therefore, R2 is our moving reference frame. Next, let's compute the position and velocity functions of M in respect to our unmoving inertial reference frame R1. This should be very similar to Physics 1 in that we add the vector O1 to O2 plus the vector O2 to M to get the vector O1M. The problem here is that we do not know O2 to M in R1. We only know it in R2. Luckily, for position, this is really easy conversion, as you can just use a rotation matrix with theta equal to the integral of the angular speed omega. Let's say you didn't do that though, and you went on and tried to calculate the velocity of O1 to M in reference frame R1. Again, you would just take the derivative of each component with respect to R1. Again though, you do not know O2 to M in R1, so what do we do in this case? This is where the magic formula comes into play. So again, the derivative of O1 to M in R1 is equal to the derivative of O1 to O2 in R1 plus this is the part of the magic formula that Dr. Frone always discusses. So this thing up here, the derivative of O2 to M in R1 is equal to the derivative of O2 to M in R2 plus angular speed omega of the reference frame 2 in respect to the inertial frame R1 crossed with O2M in R2. So, what does all that mathematics mumbo jumbo mean? Let's break it down term by term. So the first term here is ddt O1 to O2 in reference frame R1. That term is describing the motion of O2 moving away at VO2 from O1. This is actually a simple derivative, as you already know the position vector O1 to O2 in the basis ij, or in reference frame R1. So that is just a simple derivative. Next we have the term ddt O2 to M in R2. That term is describing the motion of how M moves in reference to reference frame 2 right here. So in the basis KL and with point O2 that's moving at this speed, how does M move? This is actually also a pretty simple derivative, as you will know O2 to M from your initial position function in R2. Finally, we have the term that confuses a lot of people right here, with angular speed omega of reference frame 2 with respect to reference frame 1 crossed with O2M in R2. All that is a change of basis formula from R2 to R1. And by that I mean it describes the motion of K and L with respect to I and J because K and L is moving at angular speed omega. So finally, you end with one term that's in reference frame 1, and both of these terms, once computed, you can add together to be in reference frame 2. Now, we want this to be finally in reference frame 1. So how do we do that? We actually already discussed it. It's what you could have done at the beginning here with O2M and R1. You simply use a rotation matrix or some sort of other matrix to compare the motion of I and J with K and L, and put K and L in terms of I and J. And then once you do that, you just plug that straight in, and then your whole term, once computed, will be in R1, and you are done. Let's take this example problem. Here we have a disk spinning at omega equals 3t, accelerating 0.5 meters per second squared at 45 degrees south of west, with O2 as its center point and radius of 1 meter. We also have a mass called m sliding across the disk in 1 second, as seen at the top of the screen. Let's treat R1 as an inertial frame fixed in the page, with reference point O1 and basis I1, J1. Then we have R2 as the frame that is rotating and accelerating along with the disk, with reference point O2 and basis I2 and J2. At time equals 0, O1 equals O2, I1 equals I2, and J1 equals J2. First, let's start out by doing our basis conversion between I1 and I2 and J1 and J2. This is simply a rotation matrix between the two bases, as I2 and J2 rotate at angular speed omega compared to I1 and J1. So, then you have your rotation matrix, which is cosine theta sine theta and negative sine theta cosine theta, where theta is equal to the integral of omega dt, or equal to 3 over 2 t squared in this case. Next, let's find the position O2 to M in R2. The reason we're doing this now will become apparent in a few seconds. So first, that is pretty much just sine of 30 degrees minus t and cosine of 30 degrees, or 0.5 minus t and root 3 over 2. This is because we are describing how M is moving in reference to O2. So at t equals 0, it is sine of 30 degrees away in the x direction, and at t equals 1, it is sine of 30 degrees away in the negative x direction. This corresponds to 0.5 minus t. And because it is staying at the same y value away in the j2 direction, it is only cosine of 30 degrees, or root 3 over 2. Next, let's find the position vector O1 to m in R1. We'll start out by finding the position vector O1 to O2 in R1, which is describing how O2 is moving relative to O1 in reference frame 1. So because we know the disk is accelerating at 45 degrees south of west at 0.5 meters per second squared, we can find this relatively simply. Because it is 45 degrees, it is simply negative 0.5 cosine 45 degrees, or negative root 2 over 4 for both the x and y direction. So because of this, once we take the integral twice, we get our position vector O1 to O2 in R1 is equal to negative root 2 over 8 t squared for both the I hat 1 and j hat 1 directions. Next, we need to find O2 to m in R1. If you remember from a few minutes ago, we explained that we do not know O2 to m in R1. We only know it in R2, which we found earlier. This is where you use the rotation matrix that we found earlier to come into play. For example, this guy right here. This is what we're just about to use to convert from I2 J2 to I1 J1. So we can take this guy that we found earlier and multiply it by the rotation matrix to get this, and then this is our final term, O1 to m in R1, when you add together this term right here plus this guy right up here. So this final term is in R1. So my next question to you would be, how do you find the derivative of this? Well, obviously, because we have it all in R1, you can take it with respect to t, but there is a much simpler way. The simpler way is to use the magic formula that we talked about earlier. Because all of these formulas in R2 are a lot simpler than converting them to R1, the magic formula helps us to only do those conversions right at the end. So the first term, ddt O1 to O2 in R1, is a very simple derivative, as we have this guy right here, which is O1, O2 in R1 that we just found. You take the derivative of that and you get negative root 2 over 4t and negative root 2 over 4t, and all of this is in R1. The next term is ddt O2 to m in R2. This is also very simple, as we already know this in R2, which is 0.5 minus t and root 3 over 2. The derivative of this is simply negative 1 and 0, and this is in R2, so we will have to convert this later on. Next, we have omega of reference frame 2 with respect to reference frame 1 crossed with O2m in R2. We actually already know all of these values, so this is a pretty simple cross product, with omega equal to 3t in the k hat 2 direction and O2m in R2 equal to 0.5 minus t in the I hat 2 direction and root 3 over 2 in the k hat 2 direction. Once you take the cross product of this, you get negative 3 root 3 over 2t in the I hat 2 direction and 3t squared minus 1.5t in the j hat 2 direction. As you can see, this is also left in R2, so we're about to convert this. So our final derivative of O1 to m in R1 is equal to this term in R1 plus these two terms that I combined in R2. So we're obviously going to have to convert between R2 to R1 to get this final term in R1. So how do we convert R2 to R1? Well, we did this in the position function. All we have to do is use the rotation matrix we found at the beginning that compares I2 and J2 to I1 and J1 in order to convert. And once you do that, you multiply by cosine theta sine theta and negative sine theta cosine theta. And once you're done with that, you're done, and all your final term is in R1. So yeah, that is pretty much reference frames in a nutshell. I really hope you guys got something out of this, and I hope you enjoyed.